Hello, this is Dr. Oz. Today I will talk about product mix problem, which is part of LP, which is linear programming. Let's get started. So the outline of this presentation will be why do we use linear programming? What are the requirements for a linear programming problem? Formulating linear programming problems, and then we will look at the graphical solutions to linear programming. And the learning objectives are we will formulate linear programming, we will graphically solve linear programming using isoprophet line, and we'll use also corner point method to solve a linear program. And moreover, we will talk about sensitivity analysis, and we will construct and solve a minimization problem. And finally, we will learn how to formulate a product mix problem. So why use linear programming? So it's a mathematical technique to help plan and make decisions and make, I would say, better decisions. We are trying to use mathematical models using data to make better decisions. That's the goal. And we need to think about the trade-offs in terms of allocating the resources. So we have certain resources, let's say money, employees, and so on. We allocate them different products and to make sure that we maximize our profit or minimize the cost. All right, so we will find the minimum or the maximum value of the objective. That's our goal. What's objective? Either minimize something or maximize good things. And linear programming guarantees the optimal or the best solution. Okay. So what are the LP applications? There are several. One, scheduling school buses to minimize the distance traveled. Minimize the distance traveled. Or it could be allocating police patrol units to high crime areas in order to minimize response time. Or scheduling tellers, basically, in a bank to minimize the total cost, minimize labor cost or total cost. Another application could be selecting the product mix in a factory to make best use of machine and labor hours, which is maximize profit. Another one would be picking blends of raw materials to minimize the cost. Another example could be distribution system, determining distribution that will minimize the total shipping cost, minimize shipping cost. And these are only a few examples of applications of linear programming. What are the requirements? As it says, linear programming, right? So the objective function should be linear function. So linear function is more like probably you have seen y is equal to mx plus b. It's a linear function because again there is no square terms, there is no ugly looking ln functions or polynomials and so on. This is very simple linear function. Or it could be y is equal to m1 x1 plus m2 x2 plus b, or so on. We could have more variables, of course. The presence of restrictions or constraints, we need to consider constraints, and the constraint should be linear as well to be called a linear program. And we need to have alternatives or decision variables. And these should be, as I told you earlier, all linear equations or inequalities. Let's look at an example. This could be any example, but let's give a simple example. There's a company here, Glickman Electronics. They produce two different types of products. Let's call XPod as X1 and blueberries as X2 production. So we are trying in this model maximize our profit. So our objective, which is the first component of an optimization model, maximize the profit. So let's look at the profit margins. If I sell expats, I will make $7 per unit. If I sell blueberries, I will make $5 per unit. And these are my coefficients, objective function coefficients. The more I make, the more money I make. And also I have constraints. In this case, I have only 240 hours of labor per week. In other words, maybe 6 full-time employees. And I have 2 full-time and 1/2 part-time employee in assembly department. So I have 100 hours available per week for me. And each of these products, to produce them, I need to spend so many hours. So for expats, I need to spend 4 hours per product. For blueberries, I need to spend 3 hours per unit. For in the assembly department, I need to spend 2 hours here and an hour here. And the second component, we talk about the first component is the objective, which is maximize the profit. Second component is the decision variables. In this case, I have 2 different types of decision variables. I denote them x1 and x2. x1 is basically number of expats to be produced. And x2 is denoted as number of blueberries to be produced. So these are my decision variables. So my objective function then, we said is maximize profit, but it's not enough to just say maximize profit. We should measure the profit. In this case, every expat that I produce, I make $7. So 7 times x1, this is my decision variable again, plus $5 profit margin for the blueberries. So number of blueberries produced is x2. This is my objective function value. Of course, the more x1 I produce, or x2, the more profit I will generate. So there are 3 different types of constraints in optimization. One is upper limits. And these constraints are left-hand side values of the constraint should be less than or equal to right-hand side values of the constraint. And I will talk about this in more detail, left-hand side and right-hand side values of the constraints. And we have lower limits constraints. In this case, it's opposite. Left-hand side values are greater than or equal to right-hand side values. And finally, we have equalities. And equalities, my left-hand side values are equal to my right-hand side values. All right. So for our example, we have 2 upper limits constraints. One is electronic time used, which is 4x1 plus 3x2. This is my left-hand side. Why 4x1, 3x2? Let's take a look at our table again here. So I have every unit that I produce, every expat I produce, I need 4 hours of electronic department time. Every blueberry that I produce, I need 3. So 4 times x1 plus 3 times x2 should be less than or equal to my capacity, which is 240. This is my right-hand side. This is the relationship, and these are the coefficients. And same thing I can do for assembly. 2x1 plus 1x2 should be less than or equal to 100 because I don't have more than 100 hours. So that's what I'm writing down here. Left-hand side for electronic department is 4x1 plus 3x2. The relationship here is less than or equal to my capacity. And in this case, electronic time available, which is given to me as 240 hours. So one thing is, I would like to say, right-hand side values are, in general, they are given to you. In this case, 240 hours available for me is given. And left-hand side values, you calculate them based on decision variables. I have 2 decision variables and their coefficients, okay? Second constraint here is assembly time use. We talked about that. 2x1 here plus 1x2 should be less than or equal to right-hand side value is 100 hours. So I would like to talk about graphical solutions. Although they're very nice, I'm teaching this to give you intuition, but they're really limited because you can only use them when you have two decision variables. Because if you have more, basically you cannot draw on a piece of paper. And what we do is first we convert constraint inequalities into equations. Then, once we did this, we plot the equations on a graph. Then we identify the area of feasible solutions. And then we create an isoprofit line. Then, for maximization problem, we move that isoprofit line outwards. All right. So let's look at an example. So we had two constraints. Let me just draw here y-axis and x-axis. This is my x-axis. I put number of xbots or x1. Number of xbots produced. My y-axis, I will put my x2 variable, which is number of blueberries produced. All right. So if I draw my first constraint, basically the first constraint is 4x1, 3x2 is 240. So if I put 0 in x2, then my x1 value will be 240 divided by 4, which is 60. Let's do 10, 20, 30, 40, 50, 60, 70, 80. Let's go a little bit more here. I want to have all the way up to 100, right? So obviously it's not proportional, 90 and 100. I want to do the same thing here, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So x1 is, we say that in first constraint, if I put x2 0, basically x1 is 60, right? 60 times 4 will be 240. So that's the point right here, 60 and 0. And if I put x1 is equal to 0, then x2 will be 240 divided by 3, which is 80. That's my x2 intercept, which is right here. If I connect these two dots, this is the linear line for my constraint, which is my first constraint. This is my constraint number 1. Let's draw my second constraint, which is 2x1, x2 is equal to 100. We convert again inequalities into equations. So if I put x2 is equal to 0, then x1 will be 100 divided by 2, which is 50. And let's put that 50, 0, which is right here. And if I do put x1 is equal to 0, then x2 will be 100. Right, so 100 and 0, which is right here. If I connect this 2, this is the linear line for my second constraint. This is my constraint number 2. And I know that these are not equations. If they were equations, they were these two lines, black and red line. But since these are less than or equal to constraints, basically we are talking about the area under the red is the feasible region for the constraint number 2, and area under this black line will give me the feasible region for the constraint number 1. And if you look at the intersection of these two, basically what you get is feasible region. So when you look at intersection, the feasible region is really all the way until this intersection point, all this area right here, this is your feasible region. Why can't I go less than 0, 0? Because then it means I'm producing negative number of XPaths and blueberries, which doesn't make any sense. So this green area is my feasible region. Okay, so once I am a feasible region, basically now I can move on. Let's go to next slide. So I can show you now the ISO profit line. So ISO profit line is nothing more than your profit function, which is 7x1. We say that 5x2 because profit margin for x2 is $5, and for x1, which is XPaths, is $7 per unit. So I could put different values here, and that would give me my profit. So for example, if I put x1 equals to 30 and x2 equals to 0, then that would give me $210, right? So x1 is equal to 30, x2 equals to 0, that would give me $210. Or what I could do is I could put x2 is equal to 42 units produced, and x1 is equal to 0. That would also give me 42 times 5, 210. And any solution in between these two, right? Any solution between these two would give me the same profit, which is 210. So let me show you that line. So we said 0.42, which is 42 is, let's say here, 0.42. And if I look at 30 and 0, that is basically some right here. So if I connect these two dots, this is my profit line. Any point on this linear line is gonna give me exactly the same profit, which is $210. So now what I'm gonna do is I'm going to move this line outwards. That's the next step. So I could move this line parallel to here and here and here and all the way up here and more. So if I go this way, as you see now, I exited to the feasible region. So that's not a feasible solution. So this line right here, this is not a feasible solution. But you see here, this line, this red line, has a feasible region right here at this dot. So that dot is actually intersection point between constraint 1 is equal to constraint 2. If I can find that dot, that's the area, that's the dot that my ISO profit line, which is this line right here, leaves the feasible region. So that's the best possible point. All right, so I can show you some examples here. For example, this line right here we talked about, this gives me $210 of profit for my solution, which is again 7x1 plus 5x2. And this line right here gives me $280 profit, again 7x1, 5x2. This line right here gives me $350 profit, again 7x1 plus 5x2. However, this one gives me the highest between these four lines, 420. However, this is not a feasible region anymore because 42, to get 420, I need to sell 84 X2s, that's fine, but also I need to sell 60 XPath. But I know the feasible region is around 50. So anyway, so this is not a feasible solution. So I'm trying to find the best solution. So now the key is, as we talk about, to find that intersection points. We have the constraint number 1 here, the constraint number 2. If you find the intersection point of these two, that will tell you what's the best solution for this problem. So let's do that. So I will keep the first equation the same. I first convert the inequalities into equation. And the second one, I convert inequality in equation, and also I multiply it with -2. If I multiply this term right here with -2, I will get -4x1. If I multiply -2 here, I will have -2x2. If I multiply this term right here with -2, then I will get -200. Now, if I add these two equations together, basically 4x1 plus -4x1, they will cancel each other out. So I have 0x1. 3x2 minus 2x2 will give me plus x2, 1x2. And 240 minus 200 will give me 40. So I know my value for x2 then, which is x2 is equal to 40 in that intersection point. Now, if I plug in this one into one of these equations, I can find x1 as well. So let's use the first one. It doesn't really matter. 4x1 plus 3 times 40, it's going to be 240. So 240 minus 120 is 120, divided by 4, x1 is 30. So that means that the intersection point right here is 30, x1, and 40, x2. 30, 40. This is the best dot. So this dot right here, this is my isoprofit line, would give me, if I plug this one into my profit, which is y, is 7x1, 7 times 30, plus 5x2, which is 5 times 40. That would give me the best solution, which is $410. So maximum profit that I can get is $410 by producing 30 XPods and 40 blueberries. All right. So next solution methodology is corner point method. And scientists realized that the best solution should be one of these corners, either this corner right here, or this corner right here, or this corner right here, or this corner right here. Why? So if hypothetically, if I have an isoprofit line that is parallel to x1, what I can do is I can move that isoprofit line to north, and then that isoprofit line will leave my system right here. So this would be the best solution. But let's say if my isoprofit line was perpendicular, let's use red color here, let's say this way, I could move it to the right to get a better value and better values, and this spot right here would be the spot where my isoprofit line leaves my system. Then this would be the best solution for this. But if, let's give another example, I have an isoprofit line that is more like this, I could move that line to this way, and then that would leave my system right here, right? You would get this value only if it's a minimization problem. But scientists say that, you know what, I don't need to look at every single dot in this feasible area, or I don't need to look at every single possible lines. All I need to do is look at this dot, this dot, this dot, this corner point. In this case, I have 4. Of course, if you have more constraints, you will have more intersection points or corner points. I can evaluate them and find the best solution. So if you do that, basically you can plug in these values into your objective function, and then you will get the best solution. Like if I plug in 0, 0, 7 times 0 plus 5 times 0 will give you 0 profit. And here, 7 times 0 plus 5 times 80 would give you $400 profit. And here, 7 times 30 plus 5 times 40 would give you $410. This is what we found with the previous method, the best solution, and see whether that's true again. And here, 7 times 50 plus 5 times 0 will give you $350 profit. So as you see, my best solution is right here, point number 3, as we discussed earlier, right here. All right. So now next thing I would like to talk about briefly, I have a whole separate video for sensitivity analysis, but it's important to understand how sensitive my results are to changes in the parameters. Okay, because I found my result, I say this is my best solution, but I have different parameters in this model, right? So let me just show you in the original table. So what are my parameters in this case? So this is slide 11, my parameters. These are my parameters. How much time do I need for each product in each department? And what's the profit margin? These are my parameters. These are my right-hand side parameters. So as you see in this problem, I have 8 parameters, and these parameters could change. And I'm curious what happens if I change this value. Would it impact my result? If this number changes, would it impact my results, and so on. So that's called sensitivity analysis. Try to change the parameters to see whether your final answer will change or not. So again, it could be changing the value of coefficients that we talked about. In this case, the R's per product, they are the coefficients, or right-hand side values. Right-hand side values, in this case, they are the capacities. There are 2 ways to handle this. One, try trial and error approach. Trial and error approach. So basically, I can try to change the parameters. I have 8 in this case and see whether my results will change and report that. But more smarter way to do this is called analytic post-optimality method, right? So let's take a look at it. So this is analytic post-optimality method. So after I run my model, this is an Excel solver solution. So you can see here, these are the final values. So it means it produced 30 XBots and 40 blueberries to make the highest profit. You can see objective function, which is profit, coefficients right here. So every unit I produce, XBots I make $7. So if I produce 30 of them, 30 times 7 would be $210. 40 blueberries that I produce, each of them I make $5, $200 here. So if I add $210 profit that I generate from XBots and $200 I generate from blueberries, you will get $410 of overall profit. Another thing I would like to talk about here is the second table. Here I have my left-hand side values of the constraints, and here I have the right-hand side values. I know that I have only 240 hours available in electronics department, and I have only 100 hours available in assembly department. And looks like I'm using all those times. And you can see here the shadow price, which means that if I had extra money or extra labor hour actually in electronic department, from 240 to 241, that extra 1 hour would increase my profit by $1.50. But here, extra hour available for me in assembly department would increase my profit by only 50 cents. So this is it for high level in terms of sensitivity analysis and product mix problem. I talk about linear programming here. I have detailed product mix exercise in my next videos. Until my next video, enjoy supply chain management.